So in this video, we are going to be going over areas. Now, when it comes to areas, we're talking about two-dimensional geometric figures and calculating the corresponding space that they take up. Now, with that in mind, we're going to start with the most basic geometric figure that we could possibly talk about, which is the rectangle. The area of a rectangle is in terms of its two measurements associated with it. That would be the length and the width. Area is equal to the length times the width. Length and width are both considered one-dimensional quantities, and when multiplied together it gives us a two-dimensional quantity. So talking about two-dimensional space that this object takes up. Now, quite literally, everything else that exists as a geometric figure in two dimensions, its area is based off of this formula. For example, consider a parallelogram. A parallelogram is very similar to a rectangle, except that rather than consisting of only right angles, it consists of two pairs of congruent angles. However, if I were to cut off this portion right here and reattach it right over here, you can see that we would wind up with the area of a rectangle. It is for that purpose that we refer to these two dimensions as a base and a height, and the area of a parallelogram is going to be its base times its height. This also extends nicely to the triangle. A triangle is what you get when you have a geometric figure with three sides. However, if I were to take this figure and flip it upside down and redraw it so that it has one side in common, this triangle and this triangle should have equal areas. But you'll notice that by doing this, I've created a parallelogram, and from a parallelogram I can create a rectangle. So for this purpose, the area of a triangle is 1/2 times the base times the height. Now, this does extend to particular instances like the equilateral triangle. The equilateral triangle is a triangle with three of the same side, and if we refer to each one of those sides as S, then the area of this is going to be 1/2 times the base times the height. And it's relatively straightforward to show that the height is going to be the sine of 60 degrees times that base, so √3/2. This will wind up being √3/4 times a side squared. Additionally, if we were to talk about something like a regular hexagon is something that shows up all the time in organic chemistry, to be sure, and from time to time in your math classes. Now, a hexagon of side length S can actually be split up into a total of 6 different equilateral triangles. So if you know this side length S, take the equilateral triangle formula, multiply by 6, and now you have the area of a hexagon. The idea is every single one of these area formulas that we've come up with comes back to the area of a rectangle. Now, this one's considerably more difficult to show without the use of calculus, but the area of a circle is equal to pi r squared, where r represents the one-dimensional quantity, the radius of the circle. Now, this is something that we can use techniques of calculus to show, but unfortunately we have to build up to that. So with all of these area formulas in mind, I would like to consider the following problem. Suppose that we have the graph of a function, y is a function of x. And suppose that we've been given two values that we refer to as a and b. Our goal is going to be to find the area under the curve. Now, under the curve is a very fancy way of saying between the x-axis and the function itself, in between whatever two given x values we have. Obviously, there are some ways that we could estimate this area. For example, if I were to connect this point right across here, and then connect it down to this area right here, I would have an area that's, a relatively decent approximation of what we have going on. And as long as I know this x value a, I can calculate the corresponding y value, or height, for this rectangle by plugging it in. Similarly, I could also start at the right endpoint and work my way back across like so, and come up with another pretty decent approximation for the area. Assuming that I know this x value, I can determine this y value by plugging it into the given function. Now, what I've just given you have been referred to as the left-hand approximation, and the right-hand approximation. The left-hand approximation says use the left x value to determine the height of a rectangle. The right-hand approximation says use the right x value to determine the height of a rectangle. There is another method that is referred to as the midpoint approximation, which is where we would take the point that's exactly halfway in between these two x values, which would be calculated as b plus a over 2. And then we could use that to create what's probably going to be the best possible approximation. So the midpoint approximation says use the midpoint to do exactly what we just did. To determine the height of a rectangle. Now in all three of these cases we're getting a decent approximation for the area, but it should be pointed out that if we're using the entire base, then these rectangles are not going to be good because we're going to have these big gaps where there's either no area or where there's too much area or things of that nature. Now with that in mind, each of these approximations falls into one of two different categories. The over approximation, where the calculated area is too big. We also have the under approximation. I imagine you could probably guess what it means at this point, but the calculated area is too small. Usually you can determine whether these approximations are over approximations or under approximations simply based off of taking a look at the graph. Now with those things in mind, there is a better way to come up with a better approximation. So an improved method. I'm going to try to redraw the graph that I had just created. So here's A, here's B, and again we are trying to calculate this area that's inside this closed area. So y equals f of x. So the improved method says rather than using the entire interval to approximate this area, what if we were to take this area, or take this interval from A to B, and break it up into a bunch of smaller intervals? So break the closed interval into subintervals, and the number of subintervals that we're going to use is going to be referred to as a variable called n. where each subinterval has length equal to delta x. Now delta x can be calculated. The length of the entire interval is b minus a, and we're going to split it up into n subintervals. As written up here, if we count up the number of subintervals, that would be 1, 2, 3, 4, 5, 6, 7, and 8. This would be the example of n equals 8. So what we would do is at each of these x values, we are going to do the same thing that we did on the larger scale, which is we're going to see if we can find the area on each of these subintervals. Now what this will do is it's going to start eliminating some of the extra area from over approximations or not enough area from under approximations. So essentially what we're doing is, depending on whether it's a left-hand approximation or a right-hand approximation, we are going to approximate the area on all of these subintervals using a rectangle. So select a point from each subinterval. The three most common ways to do this would be to select the left endpoint, select the right endpoint, or select the midpoint. This stands for left-hand approximation, right-hand approximation, and midpoint. Now for that purpose, what we're going to do is label these points. Your left endpoint I'm going to refer to as x0. The first endpoint after that we'll call x1, followed by x2, followed by x3, followed by x4, and continue to do so all the way until we get up to whatever our b value is. Given that there were a total of n subintervals, this will be x sub n. Now, regardless of whether it's left-hand approximation, right-hand approximation, or the midpoint, the x value that we are going to select, we are going to refer to as x sub I star. This is the representative point from the ith interval. So in the event of a left-hand approximation, in the first subinterval we would be talking about x0. In the second interval it would be x1 and so forth and so on. This value is going to be x sub I minus 1. In a right-hand approximation, for the first interval we'd be using x1. For the second interval, we'd be using x2. For the third interval, we'd be using x3. In this case, your representative point would be x sub I. And finally, if you are going to go with the midpoint approximation, then you would be looking for the midpoint between the 2 points that I just listed. That point would be the average of those 2 points. Regardless of which one of these you're going to be using, take the representative point and plug it into the function. This will give you a y value. A y value will represent the height of the rectangle. The base of the rectangle is simply going to be that little tiny change in x that you saw along the x-axis. So the area of each rectangle is going to be equal to f of x sub I star times delta x. That is a height times a base. However, you're going to have a whole bunch of these. In this example, you'll have a total of 8 different rectangles. To get the total area, add all of the individual areas. Now, this is only an approximation for the area, and in the next 2 sections we're going to be discussing how to make that approximation as good as possible.